So let's look at heat transfer through radiation in more detail. We already know that when we have an object, let's say we have this object at any temperature greater than the absolute zero, let's say temperature T, this will give out thermal radiations or heat radiations or radiant energy. We will use all these terms interchangeably. So these are giving out thermal radiations, and these radiations are nothing but electromagnetic waves, and they don't need a medium to propagate. So a medium is not required, and these thermal radiations will have different wavelengths. So basically this would be a spectrum of a range of wavelength. So let's now try to think in terms of that, how do we measure these radiations? Because in physics, whenever we come across any concept, what we try to do is basically come measure it so that we are able to compare it for different bodies. Say for example, we have another object, the same dimensions. Let's assume that we have another object of the same dimension, but it is at a temperature T dash, different from this. So that will also give out radiations. So how do the radiations of this object and this object compare? Or we have another object at the same temperature but different size, and how would their radiations compare? In order to make these comparisons and make these measurements, we have a concept known as emissive power, denoted by a small e. And what is emissive power? Let's look at the definition of emissive power. It is the energy of thermal radiations emitted by a body at a given temperature. So let's say this is the body at a given temperature. The thermal radiations given out by this body in all directions per unit time per unit area of surface. Therefore, this is given by the total radiations, let's say Q, per unit area of this object. So I will take the entire area of surface area of this object into time over here, per unit time. That is known as the emissive power of this object. And the unit of this will be joule per meter square per second. And this would be joule per second is watt. So I can write this as watt per meter square. So the term emissive power helps us get an idea about what is the thermal radiation power of this object, and then I can do a comparison with other objects. Now, if I take this object and I look at its radiation more in detail, what I'll observe is that there's an entire range of wavelength. So there's an entire range of wavelength. So if I take this object, probably the radiation that it is emitting is between the range of 100 angstrom wavelength to say 500 angstrom wavelength. So this would be say 200, 300 and 400 angstroms. So this entire wavelength range is being emitted, and now I'm interested in knowing what is the thermal radiations being emitted between this particular range or this range or this range. And to measure that, I introduce another term E lambda, which is known as the spectral emissive power. Spectral emissive power E lambda, and it is basically the same thing, Q by A by T, but I also take per unit wavelength range, delta lambda. So if I look at this definition of spectral emissive power, the energy of thermal radiation emitted by a body at a given temperature in all directions per unit time per unit surface area per unit wavelength range for a wavelength lambda. So I'm adding this over here. So what does this exactly mean? So let us say I want to find out E lambda of this particular object at 150 angstrom. So 150 will be somewhere over here. So I want to find out the E lambda over here. Now, instead of finding out the emissive power exactly at 150, what we do is we take a range. So let's say I take delta lambda, the range as say for example 50 angstrom, and that would mean 25 on the left hand side of 150 and 25 on this. So if this is exactly 150, 25 angstroms over here, 25 angstroms over here. So that range would be 125 angstroms to 175 angstrom, 25 angstrom on both sides. So this is the wavelength range of 50 angstrom that I'm looking at, and my mean or the main wavelength is 150 angstrom, and the radiant energy emitted for this wavelength or between this wavelength would be the E lambda. And E lambda would be given out by Q, which is the radiant energy embodied in this wavelength, divided by area of the object per second into delta lambda. And delta lambda is 50 angstroms. And I'm sure you guessed that if I change delta lambda, what will happen is that the spectral emissive power will change. Right, so we have talked about two terms, E and E lambda. And now let us think in terms of the relationship between these two. So if I look at this particular equation, if I look at the equation of E lambda closely, what I find is that this part is the emissive power E, Q by A by T, Q by A by T. So I can write E lambda is equal to E by delta lambda. And that would imply emissive power E of an object would be E lambda into delta lambda. So basically what I mean is that if I take a particular delta lambda, I'll get E lambda for that range. And if I keep on adding all such E lambdas for various wavelengths range, for example, this range and then this range, and I add this. So I'm adding E lambda into delta lambda for each of these wavelengths ranges. And then I'll get the total emissive power of this entire object. And therefore, we write E as integration of 0 to infinity, where this is the wavelength range, and it could be 0 to whatever we have taken from E lambda to delta lambda. So this is the relationship we get between E and E lambda. E is equal to integration 0 to infinity E lambda into delta lambda. Right, so we have seen two terms, E lambda and E, for an object which is giving out thermal radiations. In the next video, we will look at the absorptive power of an object which is absorbing thermal radiations. Thank you.